So folks, in this video here, our goal is to look at this function f of x is equal to 4x minus 5 halves sine of 2x minus 3 cosine x. We're going to look at the graph in just a minute, and then I'm going to ask you to do a rough sketch of the graph that you see. And then I'll point out that eventually our goal is to find all the x values on this graph so that the function f has a horizontal tangent line at those x values. We'll give our answer in radian form. So let's just quickly take a look at this graph here. You should have a hyperlink or a QR code to take you to that, so we could click on that here. And here you can see the graph of that function. So one thing that I've done is I've sketched the graph of the function here in red, and you can see that because of this sine of 2x and this cosine of x, this graph has an oscillatory component to it. It also continues to rise as we go further to the right, because these only contribute, because the sine cosine only output so much, they only contribute so much to the oscillation, and this causes a steady rise to the right. Okay, you can also see that what I've done is down below here in blue, I've sketched the limited domain that we want to consider. So to explain this, let me switch over to a different graph. We're after, in the final part of this question, to find this blue x point, this x point, this x point, and this x point. So we're looking for these 1, 2, 3, 4 locations where the graph of f has a horizontal tangent line, and those locations lie within this interval here, which is the interval between 0 and 2 pi. You can see that here we have, in green, another location where the graph has a horizontal tangent line, and here we have, just to the right of our domain, we've got another location where x has a again, if we were to plug this x value into the function, we'd get a point, and if we sketched a tangent line at that point, that tangent line would be horizontal. But we're not after finding those green values, we're only after finding the x coordinates of these blue points here. If I were to zoom out, you can see that we have infinitely many places where this graph has horizontal tangent lines, but we are only considering the locations between 0 and 2 pi. So returning to our paper, what I would like you to do is pause the video and do a rough sketch of the graph that we just saw. You'll have to click the hyperlink and try your best. The sketch doesn't have to be perfect, but then I want you to label the locations where it appears that f has horizontal tangent lines, and we're going to go find those x coordinates in just a minute. So pause the video and sketch this graph. So now that you've done that, let's go ahead and take a look here. Here is the main question. The whole point of this exercise is we want to look at finding all of the x coordinates on this interval from 0 to 2 pi where f has a horizontal tangent line. And we're asked to give our answer in radians. This will be a little bit of tricky algebra, and so I give you a hint here. My hint is to utilize this identity right here, and that will help us in the middle of the algebra. So recopying down our function was f of x is equal to 4x minus 5 halves sine of 2x minus 3 cosine x. And so, as we know, the derivative is a tool that tells us the slope of the tangent line. So if we want to figure out where this graph f has horizontal tangent lines, we'll take our derivative. We get f prime of x is equal to 4 minus 5 halves. The derivative of the sine of 2x would be the cosine of 2x, but then there's a chain rule, so I'll multiply by a factor of 2 there from the chain rule. And then we'll have minus 3 times the derivative of the cosine of x, which is minus sine of x. Let's take a moment to clean that up just a little bit. So the first thing we'll do is we'll say that's 4 minus, here, these factors of 2 right here would cancel, and so we would end up with minus 5 cosine 2x, and then plus 3 sine x. So do a double check, make sure that that all works for you. So the next thing, our goal is to set f prime of x equal to 0, because we're going to force my tangent line finding function, that's my derivative, we're going to force it to output the number 0 there. And so that will enable us to find the x coordinates where we have those horizontal tangent lines. So normally we would just go ahead and set this equal to 0. We'll do so now. We get 4 minus 5 cosine 2x plus 3 sine of x needs to equal 0, but I'm going to have a hard time trying to solve this trigonometric equation here. And so this is where I think I'll use this hint that the cosine of 2x is equal to 1 minus 2 sine squared x. So if I do so, we end up with 4 minus 5, and then I'm going to replace this cosine 2x with 1 minus 2 sine squared x. That was just one of our half or double angle identities from pre-calculus. And so if we clean this up a little bit, notice if I distribute this minus 5, I'll end up with, and doing a little bit of rearranging as I write, I'll end up with 10 sine squared x plus 3 sine x, and then if I collect my constants, I'll have a minus 1 there. So double check that, folks. I distributed this minus 5 to both terms, and then I went ahead and combined like terms and did some rearranging so I could lead with the higher degree term here. So folks, something that's kind of unusual, and we haven't done a whole lot in this class, is that I can go ahead and actually factor this expression here. I don't usually write this, although this is how you wrote it in, say, a pre-calculus class or a college algebra class. Notice this looks like 10u squared plus 3u minus 1 equals 0. So even though we have sine squared of x in place of u squared and sine of x in place of u, I can treat this just as if it were a quadratic. So I'm going to go ahead, usually you don't have to write that out, I'm going to go ahead and factor this quadratic equation. Well, this quadratic equation factors to be 5 times the sine of x plus 1 times 2 sine of x, and I've got a sign error. This is a plus 1 indeed, but this should have been, let me clean this out, this should have been a minus 1 here. Setting it equal to 0. Okay. So we've seen this before, folks, where we've got a product of two expressions set equal to 0. So by my zero product property, I can set either of them equal to 0. Let's start with this one here. Let's set 2 sine of x plus 1 equal to 0. Now, I'm kind of wanted to start with this one is that it's not too bad to solve this equation. We get that the sine of x needs to equal minus 1/2. And so I'm asking the question, on the interval, on 0 to 2 pi, on the interval 0 to 2 pi, where is the sine of x equal to minus 1/2? And the answer to that question is that x is equal to, well, we should draw a little unit circle for ourselves. So let's do that. So if we draw ourselves a unit circle, here's my crosshairs, and let's put that unit circle on there. So there's that unit circle. And we're asking, where is the sine value equal to minus 1/2? Well, that's minus 1/2 is down there. Let me do that in a different color. Minus 1/2 is down there. And so that would be on the interval from 0 to 2 pi. That would be at this location and at this location here. Both of these have coordinates that have minus 1/2 for their y coordinate, which is what we're looking for when we're looking for the sine value. And so what are these angles? Well, as principal angles between 0 and 2 pi, that first one is the angle 5 pi over 6. Excuse me, that's the angle 7 pi over 6. And this second one is the angle 11 pi over 6. We get those two locations on the unit circle. We know that because we have the unit circle so well memorized that we know that it outputs y coordinates of minus 1/2 at those two angles. What's kind of interesting, and the reason why I chose this problem for our review, is that it gets into the inverse trig functions here. We're also going to have to set this second factor equal to 0. So just a moment ago, we took this factor, we set it equal to 0, and we found that that happened at these two locations here. Now we're going to go ahead and set 5 sine of x minus 1 equal to 0. So let's do that. So I'm going to set this second factor here equal to 0. And so that happens when 5 times the sine of x minus 1 is equal to 0. That happens when the sine of x is equal to 1/5. Why are we in trouble now? Well, we're in trouble now in a sense because 1/5 is not one of the y coordinates that I've memorized as points, special points on my unit circle. So we still have, I mean, we could still construct the same circle as before. There's our circle right there. And then we could go ahead and say, well, let's see, 1/5 is maybe it's pretty low, maybe it's down like this. And so certainly right here we would have a point where the y coordinate is 1/5. And then again on the interval from 0 to 2 pi, we'd have a point right here where the y coordinate is equal to 1/5. And we could find out what those x coordinates were if we needed them. But I can't use my unit circle memorized values in order to answer this question. So what am I going to have to do? To find them, I'm going to say that x is equal to, first I'm going to just go ahead and introduce the arcsine operation here. So I'm going to say that happens where x is equal to the arcsine of 1/5. Okay. Now what I need to remember is that this question here says where on the interval, and then here's where we got to be a little bit careful, folks. This is where on the interval from minus pi over 2 to pi over 2 does the sine of x equal 1/5. So you need to keep this in mind when we answer the question. What I'm saying here is that when we go to use our inverse sine function, it's only going to output values that lie on this right half of the unit circle, and that's because of our restricted domain when we develop the inverse sine function. Okay? So when I plug this into my calculator is going to spit out this value right here. We're going to find the angle that gives us a sine value of positive 1/5, but that's only going to give us this one point on the unit circle, and we also need to find this one over here. We'll have to do that separately. So I took this and I plugged this into my calculator. I'm actually fine with you saying the answer is arcsine of 1/5, but just if you want a decimal approximation of that, we'd say x is, well, it was the arcsine of 1/5. And if I plug that into my calculator, I get that that's approximately 0.2014. If I want to know, that's in radians. Keep in mind that's in radians. That's not an x. That's an angle that we think of on the unit circle. So that's this angle right here. That angle is 0.2014 radians. If we go back to our image that we were working on, just as a reminder, we were looking for the 4 locations where the graph of this function has horizontal tangent lines. We found this location right here. That was at the x equals 7 pi over 6. And then we also found this location right here. This is at x equals 11 pi over 6. So we found these two values, these two x coordinates, just by using our unit circle knowledge. We have just found this location right here. This is at that 0.2014. We found this location right here at this x coordinate. If we took this x coordinate, plug it into our function, we'll have a horizontal tangent line. We still need to find this location right here. We know from the graph that we have one more to find. And that makes sense also from our unit circle analysis, because we said, hey, if we have a sine value of 1/5, there must be 2 points on the unit circle where that occurs, and we found one of them. So how do we find the other one? This is actually the whole reason for me wanting to do this problem, is how do we find that other value? So in this case, what I'm going to do is I'm going to go ahead and find this point right here, and then I'm going to reflect this 180 degrees over to land at that x coordinate right there. So I'm going to go ahead and say the other location is at x equals the arcsine of minus 1/5. Now where does that put me? That puts me when the y coordinate is minus 1/5. That would land me right there. And then I want to add 180 degrees to land at this location here. So I'm going to add a plus pi. So I can now give the 4 answers. So I can now give the 4 answers in terms of exact coordinates. They would be at the arcsine of 1/5, the arcsine of minus 1/5 plus pi, and then we had the 2 that we found early on, the 7 pi over 6 and the 11 pi over 6. Those are the 4 answers, and if I wanted to give decimal approximations of those, we've already found that this is 0.2014. And then if I plug arcsine of minus 1/5 plus pi, if you were to evaluate that in a calculator, I get approximately 2.9402. And then the other 2 exact locations, which I'll go ahead and leave in this exact form. Okay. I don't have a preference. Do you leave your answer this way or do you leave your answer this way? I don't have a preference on that. But what I wanted to point out here in this problem was how did we use our inverse trig functions to help us find 2 other locations that we knew. And that was a little bit challenging. Folks, this is a kind of an extension problem. If you're having trouble with this, please work through this and then come by and see me during office hours, and I'd be happy to help you with it. Thank you very much.